A student of mine asked me a question about the sun this week. They wanted to know what was happening inside our star to give us that energy. So let's take some time to look at our solar system, our sun, and what's happening inside that one. Because our star is so important for us, especially that it gives us light and heat so that we can live on our beautiful planet. You will see that most of the information I have for you is from NASA. NASA has an amazing quantity of information to help us, and all the links will be in the comments below, so don't hesitate to go and check them. And if it happens you have clarification questions or other questions, I can't wait to see the comments you'll have here. So let's see what we have here. So here, this is what we call solar physics, what's happening inside our sun. So something that is amazing, I noticed that there's an audiovisual engineer. His name is Lee Kobe, and he has done an animation. This is what we're going to use for this first part. So there you go. Look at how amazing this looks. So our sun is divided in three large parts. We have the core, we have here the radiative zone, and the convection zone. What we see from our planet is the convective zone. But don't forget that inside, a lot of things are happening. So first of all, we have the core here of the sun. Now keep in mind that we had at some point a nebula, and that solar nebula contracted, and at the center of that nebula, we had so much matter that we created what we call the protostar, and we had gravity that kept increasing. And then what happened with the pressure and temperature, our star was born. So here we have at the center the place where the density is the highest. We have a density at the core at about 150 grams per centimeter cube. So that's about 10 times the density of gold. Now from there, as you go towards the outer part of the core, there you have about 20 grams per centimeter cube. That means we have density of gold, so quite heavy. So if you think of gold being a solid, here we have a ball of fire, quite amazing. At the center, we have a temperature of about 15 million degrees Celsius. And as we get to the edge, we still go down in temperature, but we still reach about 7 million degrees Celsius. In that part, pressure is amazingly high, temperature is amazingly high. So we have simple particles, so protons and other particles. And what happens is with the gravity, those interact with each other, and we end up from hydrogen atoms into helium atoms. If you want to know exactly the chemistry and the formula of what's happening, tell me in the comments below. I'll be more than happy to do a video on that. So let's continue with our story. When we have two hydrogen atoms getting together, creating helium, we end up with some energy being produced. And that energy that is created in the core cannot go closer to the inside, but will start to migrate going out of the sun. So here on the NASA website, it says it can take up to 1,000,000 years for, let's say, a light ray to go from the core all the way to the outside. Other publication I have heard about 100,000 years, but keep in mind that in the core, it will take much longer than in the radiative zone. And the reason for that is that we have here at the base here about 20 grams per centimeter cube. And as we get out on the outer edge of the radiative zone, we have a density of about 0.2 grams per centimeter cube. So think about that. If you have 1 milliliter of water or 1 centimeter cube of water, you have 1 gram. So here you have 20% the density of water. So here, don't forget, this is a gas that is very hot, and gravity is keeping everything together. So here we have, as I mentioned, a density going down. We have a temperature at the core here at the edge of about 7 million degrees Celsius, and it goes down to about 2 million degrees Celsius. So still quite high. So here, this is interesting. Let's get the animation going again. And look at how beautiful we have here the convective zone. This is moving. We have the hot gas going closer to the surface. That is creating a whole bunch of anomalies with respect to temperature, anomalies with different magnetic field. So what happens is that a lot of things are going on here. And if you have a density here of the outside of the convective zone, we have a density that is, let's see if I can find the number for you. I think it was 0.00002 grams per centimeter cube. So it is, don't forget, at that time we're thinking about gas only. So here we always think of the sun to be a fireball, but it's not the case. It changes all the time. Let's see if I can look at some pictures that is quite amazing. So we have here other pictures from science.nasa.gov, and you could see that the surface of the sun is completely uneven. We have this convective zone that is churning the gas, the hot gas, all around. Here, this picture is quite beautiful. We can see how, oops, let's see, there you go. We can see how the magnetic field interact with the matter, the gas, the heat, the energy, and it's all going around like this. So this is uneven. So if you go back to the previous picture here, this one here is another beautiful example. Okay, it's coming this way. There we go. So here they call it the coronagraph. So here we have a dot hiding the sun, and you could see how much energy is happening and chaos going around the sun. So you could see here that the density around is uneven. So the question is, what is the boundary of the outer boundary of the sun? Well, it's not that simple because of all the work that is happening right here. And by the way, these pictures are from another probe called SOHO, which is a Solar and Heliosphere Observatory. Now, interestingly enough, if you can see here, you'd have a high density of material from the sun, and here you'd have low density. So energy is coming out. So the human says, okay, let's see if we can get closer to the sun to get more information. And that's when the Parker Solar Probe project came about. So let's see if we can talk about that project. So if we are thinking about this project, okay, let's talk about the machine. So we have a probe, and the probe is here with all the equipment, and we have a solar shield. The solar shield, from what I've noticed, is about 10 to 11 centimeters thick, and it's preventing the energy from the sun to interact with the probe. And when it is on its closest on here, it says that, so here we have a distance of about 0.25 atomic, let's see, astronomical units. There you go. We have a chance to see, okay, we are close. The temperature on one side is about 1400 degrees Celsius. However, on the other side of the heat shield, it is about between 25 and 30 degrees Celsius. Quite comfortable for any apparatus or equipment to work nicely. So this is what the probe looks like. So if you were to look at the mission goes like this. So let's see, I've got some information. So the mission started in 2018, and we sent the probe into space. Well, it was not that easy because we need to, first of all, calibrate this probe, and we need to make sure that we can have a consistent orbit. So here we have a great graph right here. So here we have, at this point, the probe left Earth. So here it took 7 orbits around the sun, and going back as far back as the orbit of Venus, or even going between Venus and Earth with respect to the distance to the sun. And then it created a situation where we could have a specific orbit. And here, there's another great graph here when, as the days are progressing, we could see the distance from the sun. So here, when it started, was the furthest. And here we have the orbit going closer to the sun, furthest from the sun, closest. And after 7 orbits, we were able to get a fairly consistent orbit around the sun. Now, keep in mind that the sun is very hot, So the probe gets close to the sun, gathers some data, and then leaves the sun. It's going at about 40 to 50 kilometers per second. And then when it goes back away from the sun, then everything has a chance to cool down. We don't wear off the probe too much, and it allows for the probe to send data back to Earth. So here so far, we have 17 of these orbit that has gone through. The next one is in December. Let's see, at the bottom, I have the timeline. There we go. The timeline here says that the 18th orbit comes through on the 29th of December. Let's see, is that the link? No, there's no link. That's perfect. So here we can see, so we're going to have data very, very soon. Keeping in mind that the plan is to have 24 revolution around the sun to gather data. And what I'm interested as well is what will happen after the 24th. If I look at the graph here earlier, it seems that every time there's an orbit, it's very stable, but somehow it's getting closer and closer to the sun. The question is, here we have the lifespan of the probe. Will they get to a point where they will want to get closer to the sun? And that's a very good question. Let's see what are the things they are learning as well. So here we have an example. So let's see, I think I have a good picture. Is it here? Very nice. So we saw that there is a magnetic field around the sun, and it's uneven. So that means that when we have the solar wind leaving the sun, because of the magnetic field, we have these waves of solar wind containing different quantity of matter. So let's go back to my original drawing here. So here's an artistic view when we have the probe. When it goes through different density of solar wind, different particles, or the effect of magnetic field in the solar wind, that's something that we can measure. So we have a great infographics here that shares with us what it's done. So we have here what they call switchbacks. So here what we have a magnetic field that comes out and back in the sun. But when it gets back in, knowing that we have a solar wind pushing matter out, we have these waves that are pushed out away from the sun. So it could be a wave like an S like this, little swirl depending if it is a loop. And what happens is as it leaves the sun, there's an expansion of those ripples, expansion of how they are. And this is something we can study. And we can study it for its composition, for its pattern, for its energy, which is exciting. Give me a second. I need to figure out if I can find the pictures. Oh, look at this. I saw those pictures here when it was like it could even be this year, actually. Let's see. When was this article published? So here it was published. So that's one is 2 years ago. So that means I'm sure we have better data. So we can see here as the probe got closer to the sun, how we could see different density, the unevenness of the energy, the matter, the fields affecting matter, changing as it leaves the sun. Now we know that the sun is at 1 astronomical unit from Earth, or 150 million kilometers on average from the sun. So this information coming from the sun to us has a chance to change, and being able to know what happens closer to the sun and when we receive it, that will give us information about the internal ongoing of the sun. And that's why I think it is exciting. We're getting close to the end of this video, and I found this picture here that was amazing. It is not up to scale with respect to the distance, but we could see how big our sun is compared to the planets, and how our sun can actually has such a big presence in our solar system with respect to its scale. Well, give me a second. I think I had another picture. Let's see. Can I find it? There you go. So here's an example of the distance. So if you were to look at the distance, here is 1 astronomical unit for our little planet close to the sun, and we have the other planets here. So keeping in mind that these planets are attracted from gravity towards the sun, And the sun, in many ways, are pushing energy out, and it's the nice interaction between all these astronomical bodies that makes science exciting, that makes what we do even more exciting, because if you think about it, that's the best way to better understand our sun. Asking great questions allows us to have a better understanding for future generations of scientists. So if you enjoyed these videos, please subscribe to our channel. I'm always happy um, to share new videos. If you have any clarification questions, put them in the comments. I'll be more than happy to respond to them. And on this, I'm going to put a link to another video that you might like on science, and I'll see you there.